Good afternoon, everyone. My name is Taha Amer, and as Scott mentioned, my project that I chose for this capstone project is lanes, vehicles, traffic signals, and traffic light detection using convolutional neural networks. And my supervisor for this project is Dr. Adnan. It's not switching. Okay. All right, so perception is a core concept that's used in self-driving vehicles and driver assistance systems where you want to basically make your vehicle understand the environment around it so that it can detect, objects, trees, pedestrians, other vehicles, so that, you can make the environment safe for the passengers, for the driver, as well as for the people and objects and things around the vehicle. And over the years, people have developed like several different algorithms that they can use to achieve this perception. One of which is computer vision. Then we have convolutional neural networks, which I implemented, and I'll explain that in detail in the next slide. Then we have like semantic segmentation, where you basically assign a semantic label to each pixel in the image and then put it in a different class. And then you assign that class, assign those group of pixels basically a specific class so that you can, segment them. And then you have object tracking algorithms such as like Kalman filters and other tracking algorithms like that. So if we move to all right. So what are convolutional neural networks? So convolutional neural networks, short for CNNs, are basically a deep neural network algorithm in which basically if you feed it an input image, you have several hidden layers, which are like convolutional layers, pooling layers, and you can make it as dense as possible or as shallow as possible as well. So what happens is when you feed an image, it goes through the convolutional layer. And convolutional layer is nothing but a series of filters, which you can see over here. So this is basically a filter, and this is your image that you've passed into the network. So what happens is these filters, they are specifically designed to detect patterns in the image. And these are just matrices. For example, in this case, this is a 3x3 matrix. And what happens is this your neural network takes in a 3x3 sample from this image and takes the dot product of the pixel values in this and then with this and stores the result in a new resultant matrix like this. And it keeps sliding over the image and computes the dot product and stores it in a new resultant vector, resultant matrix. And so basically what happens is this sliding mechanism, this is basically called convolving around the image. And that's where it gets its name of a convolutional neural network. So and this is just one filter. And so there are a bunch of these filters that are specifically designed to detect various patterns, such as horizontal edges, vertical edges, or different things. And once you have all these resultant matrices, you basically pool them up together. So you can use different algorithms for pooling, such as max pooling, average pooling, which basically stores, combines all the results together and stores them in a new resultant matrix. And once you have that resultant matrix, you can just feed that to the next layer, which is also called the fully connected layer or the flattened layer, which basically flattens your result, and then it forwards it to the output matrix, which basically predicts the class of the image that you passed it. So for example, I passed in an image of a car, and after all the process, it gave me a predicted class of a car. So now that we have a basic idea of how a CNN works, let's see how I implemented it in the lane detection algorithm. So for lane detection and for CNNs, we need basically a trained data set. And the data set should be as diverse as possible so that we can remove errors from it. So the data set that I used for lane detection was the BD100K lane marking data set. And it had like several thousand annotated images of road images as well as their labels. The road images were like 80 by 160 in their size, and they had 3 channels, R, G, and B. Whereas the labels, they were grayscale images of just the lane markings in that image. And the CNN architecture that I created for this particular task was my CNN had 7 convolutional layers, 3 pooling layers, 3 upsampling layers, and 7 deconvolutional layers. And so once I trained my model using the road images and the labels, and then I tested it on just the road images, I was able to get this result for the lane detection. So as you can see that it's like keeping inside the lane boundary and it's detecting the lanes. And it does struggle a bit when, for example, the conditions are not that good. For example, if you'll see over here, the road patch that's coming up, the white colored lines and the road lines, the color between them is not like that clear. So that's why it struggles for a bit. But overall, I think it keeps a good job. It does a good job of staying inside the lane boundaries. So next, moving on to vehicle detection. So again, for vehicle detection, I needed a trained data set. And so for that, I used the Crowd AI object detection data set and the vehicle detection data set that I found on Kaggle. And so both of these data sets had same labels, same columns. So what I did was I combined the data sets together, rearranged the columns to make one large diverse data set. So I have, the bigger the data set, the better. And so for this, while I was researching on how to implement this, I came across this neat library called YOLO, which is short for You Only Look Once. And this is also like a deep neural network library with a single stage convolutional network, and you can use it for multi-object detection. So the CNN architecture that I followed for the vehicle detection was it had 2 convolutional layers, 2 dropout layers, 1 pooling layer, and then 1 dense, and finally my fully connected layer also known as the flattened layer. Flattened layer. So my model, it expects road images of 64 by 64 with again 3 channels R, G, and V. And I use the pre-trained weights from the YOLO library to train my model. And so the output that I get after implementing this task was this vehicle detection. So this is the same video that I showed you before during the lane detection. But in this video, you can see that it can detect the vehicles, and it draws a bounding box around the vehicles that it finds. And let's wait for another vehicle to show up so that we can see that it can detect multiple vehicles in a scene as well. Sometimes it gets confused when the vehicle is too far or when it's not able to predict the vehicle. But overall, I think it does a good job of detecting where the vehicle is in real time. So you can see now that there are multiple vehicles, it's able to detect both of them at the same time. So next moving on to traffic signs detection. So for the traffic sign detection, the publicly available data set that I found that was good enough was the German pre-processed traffic signs. So it wasn't working on like the traffic signs that are available in US. So that's why I said, okay, I'll use a video sample from German driving footage to see if how it works. And so again, so this was a 2-step process. I first had to find or detect where the traffic sign was in an image. And then I had to basically crop out that traffic sign, feed it to the CNN model that I trained, which would predict its label. So I had to detect the traffic sign as well as recognize its label. So for the first step, I used YOLO, similar to how I did in vehicle detection, to detect where the traffic sign was in the image. And then I created a separate convolutional neural network, which had 32 filters of one convolutional layer, 1 pooling layer, 2 dense layers, and 1 flattened layer. And then once I was able to train it and test it, let me slow down this video because it's just 2 seconds. So you can see that it's able to detect the traffic signs. It does struggle sometimes because of the quality of the image or the traffic signs, and it is predicting out of 43 different classes that I had during my in my labeled data set. So like road work, pedestrian crossing, stop signs, all of these, there were 43 signs that it had to choose from, and I chose the one that had the highest probability from my detected model. So next up, moving on to traffic lights detection. So when I came to this part of my project, I came to know that YOLO, the library that I had been using, it had a newer version. So for the previous ones, I was using YOLO version 3. But when I came to this part, I realized that they have released a newer version called YOLO version 7, which is able to detect as well as recognize objects from the images. So I said, okay, I'll use this one to detect as well as recognize traffic lights. So for the data set, I use the Lisa traffic lights data set. And then from YOLO, I basically used their CNN model and fine-tuned it to my liking so that it can accept the road images or the data set that I have to train it. So it expects an image size of 608 by 608 with, again, 3 channels, RGB. And once I had trained it, I was able to get this output, which detects traffic lights in real time. And sometimes it, let me show you. Okay, sometimes it does struggles. For example, over here, you can see it's a yellow light, which is a normal light on a wall, but it's detecting it as a warning light. But overall, I think it's able to detect like the traffic lights pretty good. And so this is how the traffic light system works. And so lastly, there was only one thing left to do to combine everything together to see how it works when, so I created this pipeline, which basically takes in a video sample frame by frame, passes it through my lane detection algorithm, then through my vehicle detection, then traffic signal, then traffic light, and then gives me an output video of all the detection that it has made from the video sample. So you can see over here, it can detect the lane as well as the vehicles. And then in this video, you can see that it's detecting lanes, vehicles, as well as the traffic signs that's coming up over here, which cannot see properly, but it's detecting them. So that was my capstone project, and I'm open to any questions that you guys have. I explained it so well.
Yeah. So, can you talk about more about the various filters that you use for convolutional network?
Yeah.
Like, what was different between, like, say, lane detection and vehicle detection?
Yeah, right. So with different filters, people have like already made these filters that you can use. You use. So for example, people have made filters to detect edges from an object. So you have vertical edge filters, you have horizontal edge filters, and the filters are nothing but just a matrix with predefined values that they've calculated through various statistical formulas and such. So you just search for a filter that can detect, let's say, horizontal edges or vertical edges or diagonal edges, and you just apply it to your input image, and it'll give you an output of the edges that it was able to find based on the filter that you mentioned.